So this lesson is very procedural. We're talking about a thing called the first derivative test, which is basically something you use to find the relative maxima and minima of a function. And the basic idea is what I have outlined here. It goes along with what I said in the previous video. If you've got the derivative of a function, and if that derivative changes from positive to negative at a critical number, and if the function exists there, then that value you found is a maximum of the function. And that should make sense, right? What does it mean if the derivative changes from positive to negative? That means the function changed from increasing to decreasing. And so what must have happened up there at the top? There must have been a maximum, right? Similarly, if you've got a derivative that changes from negative to positive, well, that should mean that the function is changing from decreasing to increasing. Well, then clearly what happened is you hit a minimum value, right? The last thing that can happen, what about if the derivative changes from negative to negative or positive to positive? So what if the the derivative is coming down negative and then it levels off and then continues to be negative? Or if you've got a derivative that's positive and levels off and becomes positive again, in those cases you don't get a maximum or a minimum. In fact, what you get is something called a saddle point. When you've got a curve that sort of does something like this, or a curve that does this, these points are places where the derivative is zero, where you've got a critical point, but it's not a maximum or a minimum. It's called a saddle point. So in short, if the derivative changes from positive to negative, it's a maximum. If it changes from negative to positive, it's a minimum. And if it doesn't change, if it stays negative or stays positive, you've got something called a saddle point. In the next slide, I'm going to sort of go through the 5 steps in the first derivative test, and I'm not going to walk all the way through them to keep the video shorter, but those are the steps that we're going to use. So let's take a look at those. So I promised steps, and here they are. I found when we did our chapter 6 problems that numbering out the steps makes a really big difference. A lot of you, I noticed in all your problems, you were writing down step 1, step 2, step 3, step 4, and it was really helping you guys. So I'd recommend you write these down and get used to using them. So I'll quickly run through the procedure. Step 1, find the critical numbers, because as I mentioned in the previous video, that's the only place you're going to find max and min. So first, find the critical numbers. Second, break the domain into subintervals, and I'm going to do an example of that in the next slide. You'll see that. On each one of those subintervals, you're then going to pick a number and plug that into the derivative. And basically look for whether it's positive or negative, which should mean whether the function is increasing or decreasing. Right? Then, anytime that it changed sign, your next step is to plug that number back in to find out if it exists. And the last step is going to be to sort of write a sentence about what happened. So I've got 2 examples here lined up, and we'll take a look at those, and hopefully this will all make sense by the end. So let's jump right into it. So I want us to find and classify the extreme values of this function. F of x is 3x to the 4th minus 8x cubed plus 36. So hopefully you recall step 1 in this process was to find the critical numbers. Find the critical numbers. And the way I do that is by setting the derivative equal to 0 or looking at where it's undefined. So first I'll take the derivative. F prime of x is 12x to the 3rd minus 24x squared, and the 36 just goes away. Note, this function is never undefined. The one major cause of a function being undefined is division by 0. This doesn't even have division. So really all I need to look at is where is this equal to 0. So I'll set it equal to 0 and I'll factor 12x squared times x minus 2. So my critical numbers are 0 and 2. Right? So yay, step 1 was finding the critical numbers. Step 2 was to set up subintervals. Now what does that mean? This original problem didn't come with a domain. It didn't give us specific values that we needed to work with. So because of that, we assume that this function is working on all real numbers between negative infinity and positive infinity. So for this step where you set up subintervals, you sort of start all the way on the left with negative infinity. Okay, so I start with negative infinity, and from negative infinity I go, imagine an infinitely long number line. I start at negative infinity, and I go all the way until I hit one of my critical numbers. So the first one I'm going to hit is 0. right? And then I stop the subinterval there. Then my next subinterval is going to go between 0 and the next critical number, which in our case is 2. Right? Then I'm going to go 2 until I hit my next critical number, except there aren't any more critical numbers, so I keep going until I hit the end of my interval, so infinity. So you almost imagine here you've got a number line that's going from negative infinity to infinity, and you've got special numbers at 0 and 2. What you need to do is simply write down, hey, my first one goes from negative infinity to 0, my next goes from 0 to 2, my next goes from 2 to infinity, right? The next step, right, step 3. I don't want to use yellow for this one. Step 3 is to plug in, so plug a number from each interval, from each subinterval, into the derivative, right? And fortunately, we've already found the derivative. Right up here, we found this expression for the derivative. So what I need to do is for each one of these intervals, these 3 things, I need to pick a nice, easy, convenient number on the interval. And you can't use the endpoints. You can't use 0 or 2 or, of course, the infinities. So for this first interval, I'm going to choose -1. Why? Because it's a nice, easy number. On the next interval, I'm going to choose 1. And on the last interval, I'm going to choose 3. On this interval here, you could have chosen a half. You could have chosen 3/4. 1 is nice, so I'm going to pick that one. Over here, if you want to pick 5, that's fine. I tend to choose the nicest, smallest, easiest number I can find. Now, I want to point out, you've got one derivative up here, but you may find that it's easier to actually plug into the one that's been factored. And there's kind of a good reason for that. I now want to plug -1 in up there, right? So how do I do f prime of -1? When I plug -1 into this factored version, I'm going to get 12 times -1 squared times -3. Right? So that gets me 12 times +1 times -3. And note, this is what's important. I really don't care what that number is. What I care about is the fact that the derivative, f prime of -1, is negative. Right? And why do I care about that? I care about that because that fact means that my original function is doing what? F of x is decreasing. Right? So that was my work for the first interval here. I now need to do a similar thing for each of these other 2 intervals. Right? So I need to do f prime of 1, and I'm totally going to run out of space here, but I'll do my best. When I plug in 1 to that 12x squared expression, 12 times 1 squared times -1. Again, it really doesn't matter that this was -1. What's important is that f prime of 1 was negative, and that means that the function on this interval is decreasing. Right? The last subinterval, we need to do the same thing. I need to do f prime of 3. I'd encourage you to pause the video, try that out on your own. When we plug this in, we end up with 12 times 3 squared times 1. This is 12 times 9 times 1. Again, it really doesn't matter to me that that's 108. What I care about is the fact that f prime of 3 is positive. And what does that mean? That means that my function is increasing. Right? So that was step 3. Step 4, and I don't think I gave it a pretty name before. Step 4 is basically look for changes. Right? This one was decreasing, this one was decreasing. So what happened here at 0? This was probably a saddle point. Saddle point at x equals 0. Right here, I'm going from decreasing to increasing. So what does that mean? That means that there is more than likely let's see, decreasing and increasing means it was decreasing and then increasing. Means there's probably a relative minimum at x equals, let's see, what was that value? This value up here was 2. So a relative minimum of x equals 2. The one other thing that we need to do at step 4 is we actually need to plug that back into the original function and find out if it really worked. So what is f of 2? Well, my original function was, there it is. It was 3 times 2 to the 4th minus 8 times 2 cubed plus 36. If I plug all that stuff in, we should end up finding that it's 12. Step 5 is where I'm supposed to make a conclusion. My conclusion is basically that there's a saddle point at 0, 36. I didn't show it up here, but I should have done f of 0 and found out that that was 36. It's really easy. And the other thing is that there's a relative minimum at 2, 12. And yay, we did it. Long problem. They do get faster as you work through them, and you're not going to have a whole lot of them in the homework. I'm going to try and keep them fairly short. I have one more example that I'm hoping is going to go faster than this one, so I've got that coming up on the next slide. Let's take a look at that one. So here again, same instructions. I want to find and classify the relative extrema of this function. So remember that step 1 is where we're supposed to find the critical numbers. So that's where I take the derivative. Derivative of this thing is low d high, which is 1, minus high d low, which again is 1, square the bottom, and that's our derivative. So f prime of x is negative 1 over x minus 1 squared, right? Is this thing ever undefined? It is. It's undefined at x equals 1, so that's a critical number. Is this thing ever equal to 0? Well, a fraction will only ever be equal to 0 if its numerator was equal to 0, and that's negative 1, which means that doesn't happen. So my only critical number is 1, right? So that brings me to the second step. The second step in this process is where we set up our intervals. Right? My intervals go from negative infinity until I get to my critical number of 1, and then from 1 up to positive infinity. Great. My next step, which I think I used green for, my next step was to evaluate f prime of x. And remember that f prime of x was negative 1 over x minus 1 squared. So on this first interval, I'll choose 0, I choose u, and on this interval, I'll choose 2. Right? So great, now I just have to do what is f prime of 0. F prime of 0 is negative 1 over negative 1 squared. That means it's negative 1 over 1. That means f prime of 0 is negative. And what does that mean? What does that tell me about f of x? F of x is decreasing. Right? Let's look at the other interval, and I like to draw lines through these things so you can separate your work. Over here we'll do f prime of 2. F prime of 2 is negative 1 over positive 1 squared, which is negative 1 over 1. F prime of 2 is also negative. And so that means that f of x is decreasing. Okay. Step 4 is where we're supposed to look at change. Change. And notice here we go from decreasing to decreasing. What happens when our function goes from decreasing to decreasing some more? Sometimes it means that there's a saddle point. The only way to find out is to take your number and plug it back in. So my critical number, remember, was x equals 1. And my original function, f of x, was x over x minus 1. When I try to plug in 1, I get 1 over 0, which means there was an asymptote there anyway. So this thing isn't even a saddle point. At this point, I'm wishing that I knew what x over x minus 1 looked like. We know it has a vertical asymptote at +1, and it has a horizontal asymptote of 1. I wouldn't expect you to know that offhand. In short, I'm pretty sure this graph ends up looking like this. So what happens is the function is decreasing, 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 asymptote, and then decreasing, 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 decreasing. So it had this critical number in here, but we didn't get a chance to see, like we didn't get a saddle point because it didn't even exist in the original function. And that's a key point. If your function doesn't exist for the critical number, it can't be a maximum or a minimum or a saddle point. This has been a long video, and I'm done with this one. We'll see if there's another one.